Hello, a warm welcome from Denver to everyone across the globe who may be viewing this. Thank you for your wonderful support during these very difficult times. I will be presenting this talk on behalf of my co-authors and also colleagues whose name do not appear here, but have made significant contributions in making this presentation happen. The outline of this talk would comprise an element of similarity and differences between traditional geophysical inversion and machine learning, and also show how that leverages significant gains in mathematical formulation and piggyback on ever-improving computational efficiency to solve larger scale practical problems. We will be presenting inversion results on synthetic data and also two field data inversion results of increasing size and complexity to highlight the ever-increasing practicality of AI-based methods. I would like to thank Professor Mark Everett of Texas A&M and also Ron Bell and Bill Barkhouse of Drone Geosciences for providing us with these data sets. We will start with the well-known, widely used Tikhonov parametric functional, and I'd like to draw your attention to the stabilizing functional S on the right, and that acts on the model parameters aim. Imposing the a priori constraints on what model parameters can and cannot do as inversion tries to minimize data has been both a blessing, but also sometimes a millstone in several complicated geologic settings of increasing commercial significance. Machine learning, on the other hand, uses a similar equation to the Tikhonov parametric functional for training the models, but with one key difference. The stabilizing functional now no longer requires an explicit compliance of model parameters to observe certain pre-existing mathematical relationships. And if we can overcome the computational hurdle associated with machine learning, then this freedom can be a game changer in several geologic settings. Now, the sensitivity to fluid electrical conductivity to make electromagnetic methods an attractive choice for monitoring the efficiency of fluid floods has been ongoing for several years. However, the accuracy and resolution using traditional inversion methods have long been a bottleneck for a widespread commercial application. Now, in this example, published in Geophysics last year, Daniel Colombo and his colleagues show that with machine learning, dramatic gains are possible in this arena. However, the computational operations typically needed to make this happen at field scale is likely still quite expensive for most operators. So now, if we take a look at the different flavors of deep learning neural networks, the dense node network, or DNN, on the left, and the convolutional neural network, or CNN, to the right, and combinations of these two are amongst the most commonly used neural network architectures in the geoscience industry today. It has been reported by several authors, notably Vladimir Pusirev and Andrei Swidinsky and others, that DNNs are relatively quick to train, but are difficult to generalize too far outside the range of models that it trains on. CNNs, on the other hand, can take somewhat longer to train, but generalize better than DNNs. Now, the Z-directed magnetic field sensor response for a buried cube, dominantly magnetized in the same direction, is a classic potential field simulation exercise that is used for validating new inversion methods. Now, in this instance, the machine learning model trained 1,000 different responses due to variations in cube susceptibility and background susceptibility. And as we can see, even with laptops, this is a comparatively trivial computational exercise that completed in less than 8 minutes. Now, the inversion results shown in the bottom left and right panels show a remarkable similarity to the point of being indistinguishable from their true models, even when no constraints are imposed. Moreover, the system literally trains in the blink of an eye. So to summarize, we trained 1,000 models in 8 minutes, trained a deep learning neural network, and predicted results in 7.8 microseconds, and all of this on a Dell laptop. So what's the catch? As most of you would have correctly surmised, it is indeed an inverse crime to recover models on the same mesh in which the training samples are generated. So rerunning this exercise on a more generic mesh shown on the right, we observed that the basic metric of the average model and model training and test parameters, which are on the x-axis, are quite similar to the predicted values on the y-axis, which are indicative of a well-trained network. However, the recovered image is no longer a sharp boundary cube, but rather a smooth, diffuse image reminiscent of model recovery using conventional least squares methods. So yes, machine learning is also not immune from the age-old curse of dimensionality that has plagued geophysicists for generations. Now, revisiting the CNN architecture, we see that it trains by learning the different features present in the models using the different layers of the network. The shallow layers teach about the simpler features, while deeper layers train on the more complicated ones. However, the fundamental issue of far fewer data points than model cells remain. Most workers, notably Puzarev and Sudinsky and others, have adopted an incremental transition from data dimensions to model dimensions through a combination of choices in upsampling, cropping, and other methods to eventually match the dimensions of the target vectors. However, in this study, a different approach to this issue was adopted by studying the conventional inversion practices of using joint operators. They are known for their ability to project from data space to model space and are ubiquitously applied in all geophysical methods. The projected data has the dimensions as the same dimensions as the target variable or the model vector. And this makes it much easier and efficient to design training architectures that can mitigate some of the dimensionality issues encountered in geophysical inversion. Now, a key metric when training is to compare the loss values of the training and test datasets as it learns to predict the target variables better and better with each passing epoch. And as long as the training mean squared error keeps pace with its decline pattern with the test mean squared error shown in orange here, the train being in blue, we are neither overfitting nor underfitting the data. In addition, while not unique, the comparison of the average cell value to true model cell value on inversion can provide a sanity check on what's being inverted. Now, compared to the previous inversion, we see that the convolutional neural network has resolved the top and the sides of the target quite clearly, but the base is not yet quite well resolved. But as the training continues and the mean squared error diminishes further, we begin to see that the base of the target is also beginning to get a better result. With that, we move to the 3D inversion of field magnetic datasets, and we start with the Washington and Brazos State Historic Site located near College Station, Texas A&M. And the data was collected by A&M students under the guidance of Professor Mark Everett. A key processing step involves the removal of the deeper influences and conversion to absolute amplitude data to focus the attention on the absolute susceptibility values of the buried near surface targets without regards to their direction of their magnetization. Of particular interest, of course, are the 4 circular anomalies that are present in the dataset and the likelihood of being caused by a buried pipe. Now, buried pipes and other cultural debris are usually magnetized along their individual dominant axis, unlike rocks and other geologic materials, which are frequently aligned in magnetization direction or with the ambient geomagnetic field. Now, as seen here, the combined response from these variously directed magnetized elements in the bottom panels approximate the observed magnetic field in both TMI and absolute amplitude space shown on the top panels. Due to the complications arising from these various directions of magnetization, a good first approach is to train the network on predicting just the absolute susceptibility values. We start with the minimum norm least squares inversion using the Memorial University codes. And we're looking at here the vertical cross section right through the center of those 4 anomalous field values noted in the data. The vertical cell boundaries are spaced about at 0.5 meter intervals. So the inversion shows the target to be roughly located somewhere from the top near the ground surface to about 3 meters below. Now, ignoring the typical inversion artifacts that are associated with vertical resolution issues, in general, the inversion does not show any significant anomalous target existing below 5 meters. And that enables the setting of the inversion domain for the deep learning neural network based inversion. We see a more compact location and distribution of the anomalous target. For interpretation convenience, the values are normalized to relative absolute susceptibility values in the range of 0 to 1. In order to capture some of the more subtle features in the inversion, the upper limit of the color scale is being capped to 0.06. We can see that the top of the pipe seems to be located very clearly and showing where it's potentially connected to up with the separate magnetic structure on the right, and how it is not connected at the bottom. There are also some discontinuities in the middle, and some of which is related to room for improvement in the training of the data, while most of it, as we'll see in the next slide, is related to a sharp drop in the anomalous susceptibility content. By stripping out the very low background susceptibility values, this image becomes more interpretable in 3D. You can see that the linear and tubular nature of the pipe is quite clear, when the difference in susceptibility values along the resolved material thickness along the axis of the pipe are indicative of either corrosion or pipeline discontinuity. It can also be due to non-magnetic material of the pipe, which then brings us to the next issue of validation and business significance. Now, for unknown cultural targets, it is difficult to assign magnetization directions to the inferred model from the trained weights and forward compute the response and compare the predicted data to observe, like we do with traditional inversions. For gravity fields, this would not be an issue, as density is essentially a scalar quantity. So now, in the absence of a more sophisticated network that trains on both susceptibility and magnetization, the next best option for a sanity check is to compare the recovery of a known target that was not provided during the training of the network. And so here we have this pipe-like target generated on a specialized mesh. And the data from this was used to see if this pipe-like target can be recovered on the more general mesh on which the data trained on. And we can see that the trained neural network model passes this test quite successfully. Now, the improvements in image recovery from traditional methods using AI does open up the possibility of asking questions that previously were off limits to surface-borne magnetic data. The conventional inversion we can see here, it does a pretty good job of clearly identifying where the buried target is, and it's most likely a pipeline that's located, let's say, somewhere between 0 to 3 meters below surface. But looking at this image, not much else can be inferred. Whereas with deep learning imaging, we can start asking questions about pipeline continuity, thickness variation, corrosion, and others that are currently addressed by pigging, which is essentially putting a sensor in a downhole inside the pipe. And that is an order of magnitude more expensive than acquiring data from the surface. So with deep learning imaging, we can essentially replicate some of the functions that are currently done by pigging at a scale that won't be as high resolution, but maybe good enough for making some rudimentary business decisions at a fraction of the cost. Now, scaling up this to larger data size and larger pipes, one such effort was undertaken by Drone Geosciences when they collected very high resolution magnetic data over an unannotated field in California. We are offering a sneak peek of the results here. More detailed presentation on this data set will be made at the SCG Drone Summit in November. Now, when we look at the satellite image of the survey area, there is nothing exposed on the surface to indicate the existence of buried pipes. Prior to the data acquisition, there was no existing knowledge of buried infrastructure of any kind over here. The acquired dataset is approximately a 40-fold scale-up in size compared to the prior dataset. And the flight height above ground level in the middle picture here increases from left to right, while the surface topography, which is the left panel, has an opposing gradient. And this, of course, complicates the interpretation of the observed magnetic data through visual means. Now, skipping past the almost standard processing steps of stripping out the regional and deeper contributions to the magnetic field, the final depopulated dataset contains about 2,000 data points for inversion and is shown here. The service topography in the middle panel here is just flat for all practical purposes within that inversion domain. And also, preliminary modeling confirms that most of that high amplitude residual magnetic anomaly can be understood in terms of two separate buried pipes with an upscaled 1 meter rectangular cross section. So with that, we come to the inversion results through neural networks. And we've identified that based on the model results, that the inversion domain can be set within a narrow confined zone of the final depopulated dataset. We are looking at the thresholded distribution of normalized absolute susceptibility values in plan view. And the threshold limits are set to 0.0075 to 0.008 to make this almost an isosurface view of the subsurface. The red colored zones show a credible potential buried pipeline or other metallic debris that are longitudinally aligned within the surveyed area. And as the modeling suggested, the inversion does seem to pick up two separate pipelines with some jogs and bends in them. And it is also possible that the jogs and bends are really related to a third pipeline coming down from the top of the section. There's also some evidence of pipeline discontinuity or corrosion that can be inferred from this view here. Now we'll talk more about the efficiencies of using high performance cluster machines that make generating inversion results from these relatively large size data sets possible. But first, let's take a look at the inversion results a little bit closer. And looking at this from a slightly oblique angle, we can potentially identify 2 to 3 major pipe-like structures with some jogs and bends. The top of the anomalous targets is frequently buried shallow within the top 50 centimeters and will become more readily apparent in this 3D animation video that we have for you. In this video, we see that the anomalous bodies are much closer to the top of the surface instead of the bottom, which is set at about 4 meters below ground level. There are some places where the top of the target dips to about 1 to 1.5 meters. And also the jogs and bends in the apparent pipe-like geometry are quite apparent right here. Now, before wrapping up, we wanted to highlight the fact that comparing the size of the problem solved to the computational resources used, we can infer that the interpretation of this latest project represents almost a 40 times scale up in data acquisition and over an 18-fold scale up in the size of the training matrix. Utilizing high performance computing resources, we were able to complete this project at a comparable level of accuracy with a nearly 250% reduction in computation time. This represents savings of roughly 2 orders of magnitude for both data generation and training models. So in this talk, we traced the development of full 3D inversion using deep learning neural networks from concept to practical scale deployment. The generic scheme is sensor and scale agnostic and very friendly for extension and adoption to many geophysical and non-geophysical applications. The key algorithmic and computational efficiencies discussed in this presentation enables practical scale results in a matter of days for many applications. And eventually we expect to do this near real time. We are currently looking at opportunities to validate the inversion results with ground truth verification via either the drill bit or excavation. Please feel free to contact us if you have such an opportunity in mind. We would like to extend our thanks to Ron and Bill again for providing us with the data set and support in many of our endeavors. Special thanks to Hormuz for helping out on a critical part of this project, and to Mark for providing valuable suggestions in addition to providing the Washington and Brazos data set. To Ruth and Catherine for enabling access to the State Historic Site for collecting data. And last but not least, thank you to the management of EmPact-AI, RocketML, Memorial University, and Mount Allison University for resources to support this work. With that, we conclude this presentation and we'll be happy to take questions during the in-person version of this talk. Thank you for listening.